Hello, my name is Gohenthan Krishnan. My student ID is 2024-3799. Welcome to this demonstration of Langton's and a cellular automation simulation where simple rules create complex patterns. In this video, we will walk through the code, explain how the system works, and showcase how ants moves across the grid following simple instruction. The system is divided into different components: the AND class, the grid class, and the graphical user interface. I will also demonstrate how the ants interact with the grid, how we control the simulation, and how we can analyze the results. Let's dive in. The AND class. The AND class defines the behavior of each ant in the simulation. Each ant moves according to Langston's ant rules. When it encounters white cell, it turns right, flips the cell to black, and moves forward. If it's on the black cell, it turns left, flips the cell to white, and moves forward. The the ant can face four directions: north, east, south, and west. The direction is controlled using an enum, which allows us to easily rotate the ant's orientation. This class also ensures that when an ant moves beyond the grid boundaries, it wraps around toroidal grid behavior. And the code updates the grid size and adjusts ant's position if necessary. The ant class handles the core logic for the ant's movement, direction, and interaction with the grid. This class is fundamental to the simulation as it defines how the ants behave based on the grid cells they encounter. The grid class The grid class manages the grid on which the ants move. This class defines the grid size and it handles grid expansion as the ants move beyond the initial boundaries. The grid is partitioned into smaller sections to improve memory efficiency and performance. This partitioning allows the system to process updates in parallel using fork join pool, which speed up the simulation, especially for larger grids. And this is a code for the core grid properties, performance monitoring metrics, the dynamic grid bounds tracking, and calculate the cell key within a partition. This grid also tracks how many cells, updates, and partition access have occurred, providing us with performance metrics monitor how simulation is running. Updates the grid bounds and expands the grid if necessary. Support for that. Splits the work into four quadrants for the parallel processing. The grid class ensures that the simulation is efficient, scalable, and able to handle large grid sizes. It optimizes performance using partitioning and parallel processing, making sure the system runs smoothly even with many ants. The single thread execution with multiple samples, the for that. The multi-thread execution with multiple samples. So Record the individual operations for detailed statistics. The Langtons and GUI. The graphical user interface is where users interact with the simulation. The canvas displays the grid where each cell is either white or black, and ants are represented as red circles. The GUI allows you to zoom in and zoom out the grid using the mouse, scroll, or keyboard shortcuts, which makes it easier to explore simulation at different scales. The control buttons, the UI components, the keyword direction variables, the keyboard zoom control, and set up the canvas and its zoom in functionality. Handle zoom operation with bounce checking. And in the simulation controls, in the simulation control you can start the simulation, pause it, and reset the grid. There are also buttons to add the ants to the grid, remove ants, and adjust the speed of the simulation. You can also toggle the grid visibility and change the grid size using the provided controls. Next, uh, performance monitoring and optimization. Performance is key simulation with large grids. To track and optimize performance, we use performance tracker and performance report classes. The performance tracker monitors the time taken for operation time like grid updates and ant movements. It also compares the performance of single thread versus parallel execution. We track memory usage and system resources, providing insights into how efficiently the simulation is running. The performance report generates detailed reports showing execution times, memory usage, speed up ratios, and efficient metrics, allowing us to analyze the system performance. Next, I'm going to run this system. Terminal, install. This is the GUI. Here we can add and remove ant. Also we can add the random ant, remove the ants, and we can set the grid size here, and the start, pause, or reset, and increase the speed control, and performance tracking report. Pause and reset. Now I'm going to start this. will take some time to get that highway pattern. So we have to wait until that. We are close to it. As you can see that ant has now formed a highway. This occurs when the ant moves in the same direction for significant numbers of steps, creating a repetitive and stable pattern. This is an example of emergent complexity where simple rules lead to complex behavior. Once this pattern is formed, we can pause simulation and serve the final grid configuration. We can serve this grid, and this highway pattern demonstrates how Langton's and evolves from randomness to stable, predictable behavior. We can pause the we can pause the simulation and we capture this pattern for review. We can That's what I saw you before. In Langton and is a fascinating example of how simple rules can create complex emergent patterns through parallel processing, efficient memory management, and real-time performance monitoring. We can scale the simulation to handle large grids and many ants. We have explored the ant class, grid class, GUI, and performance tracking, and all of which work together to create dynamic and scalable simulation. Thank you for watching. I hope this demonstration helped you understand the Langston and simulation and how it works. Thank you for watching. Thank you.